Bueno, yo os vengo a contar un poco una investigación.
I'm going to speak about a research at University of Zaragoza with Jorge García de Quirós, who was finishing his university studies. Our work is Tor protocol modeling and structure of hidden services characteristics. This is me, and this is Jorge. I would like to thank Francisco Montserrat Rodríguez for providing us with machines in order to carry out this research work. I'm going to explain what Tor is. Have you ever used Tor, or do you know what Tor is? Great, I like that. The first contribution of our work is modeling the Tor network. Here you'll see Uml diagrams. I know that many of you are not software engineers, so I won't get into detail. However, the slides will be in the internet, and the extensive work we've done is uploaded, so you can check it if you want. The second contribution of our work is carrying out some work for de-anonymization Tor Hidden Services. We call this Tor HSS scanner, playing with the things that our tool does, and then I'll speak about related work and my conclusions. First of all, what's Tor? It's a network which has been specifically designed to improve the user's anonymity and privacy while navigating the internet. It was initially developed by the US Naval Research Laboratory with the aim at protecting government networks in the US. Today, this network allows journalists to communicate, or activists who are in dangerous areas in an anonymous way. It allows the state, for example, to carry out undercover operations or surveillance operations, and of course other type of strategic or military operation. Currently, Tor network is maintained by an NGO in the US. So if you donate to this NGO here, you don't get tax reductions. It's called the Tor Project. They do three things. First of all, they develop a specific browser, which is a modification of Mozilla Firefox. Those of you who use Tor, did you do it 10 years ago or now? Because now it's completely different. Now it also manages the protocols of Tor network, and it controls the network status. This organization is trying to avoid the fact that, the Tor network uses many nodes, and they they make sure that these nodes are not linked to specific states, which could be dangerous. How does it work? Tor network is going to provide us with this communication system based on virtual circuits with low latency and anonymous. The intermediate hop is going to take place through a node. I'm going to create a virtual circuit between different nodes of this network. What does this guarantee? Well, basically it guarantees that there's no direct relation between the client and the server. So that ensures that guarantees that connections are anonymous. Each node only knows about the next one and the previous one. That's the privacy of the communication. Something else which is also important, all the traffic through Tor network is encrypted in layers. That's why it's called onion routing, because you have many layers like an onion. Let's imagine I have node 1 that wants to communicate with node 4. I have this bunch of nodes. Node 1 will create a communication channel with node 2. This node 2 will create a communication channel with node 3. And finally, this other channel will be created. Each of these layers means that it's encrypted. And why do we need Tor? That would be a good question. Some people can use it, for example, for weird failures. Porn with dwarves, porn with animals, any weird thing you may think of. The use of Tor network has a legitimate purpose, which is guaranteeing the freedom and the individual rights and freedoms of individuals. In other words, access to censored material in specific countries. If we were in China, for example, they have a firewall in the internet called the Red Firewall, which filters any type of communication that goes outwards. What do they filter? If we were in China and you Google Tiananmen incident, you wouldn't find anything. It doesn't mean that there are no results in Google. Basically, China is filtering the results to remove them. So if you live in that type of this type of countries and you want to access this type of materials, they should do it through Tor. It's also useful for victims of sexual abuses or rapes. There's some sort of psychological support. There are thorough chat rooms in which this type of victims can express their fears or their feelings with people that have suffered the same experience. There is some sort of support group, and of course, for whistleblowing anonymously, anonymous whistleblowing against states or companies. But unfortunately, there are illegitimate uses. This is one of the things by which Tor is known for. This is an image from a forum called Silk Road. It was basically an online drug market. You could buy any drug. It was 24/7 dealer. This service was launched in 2011. It was closed 2 years later by the FBI. Its founder, Red Pirate Robert, is in jail in the US. Double life sentence plus 40 years in case he escapes, without possibility of parole. So you can have an idea of the business this far had. Today, Tor is used for not just for this type of activities, but any type of illegal activity you may think of. Selling weapons, child porn, hiring mercenaries, guns for hire. I wanted to show this picture with the iceberg. I would like to speak about hidden services. What's a hidden service? It's Google, but you can only access Google through Tor network. That's a hidden service. It's a web server which you can only access through Tor. This offers me double blind. I don't know where the web server is located. I don't know. It's not like a regular server. You have the IP, you can serve it in China, Korea, Germany, whatever. I can't know where the server is located, and I can't know who's accessing the server because it goes through Tor. That's the advantage of hidden services. A hidden service is any address you find on the internet that ends in .onion. The INA officially recognized this dominion in 2015. Currently, if you visit this website, Metrics, Tor Project, they have the daily statistics of use of Tor network. Currently, it is made of 6,500 nodes. So far, there are 2 million unique users, and on average, there are 115,000 hidden services. In other words, services we don't know what they are. This iceberg is here to show what's the visible network, which is most people know, then the deep web, which is the web which is not indexed by search engines, and then the dark web, which are services which you can only access through Tor. I've taken this image from the internet. It's from 2015 and it shows the average users per day, per country. There are many people in the US, in Germany, France. There are some research papers that have analyzed the content of hidden services with a little bit more of detail, just using email accounts, and coincidentally, these bigger countries are the addresses that you tend to use out there, and also universities. The top 10 users: United States, Germany, Saudi Arabia, United Arab Emirates, Russia, France, Ukraine, etc. Well, let's speak about modeling to keep track of time.
Daros que hay un montón de trabajos.
First of all, we should know that there are many research studies and papers that have studied Tor protocol. So these are academic papers. However, I said to myself, well, we have Tor network. We more or less know how it works. But when you read the specs, you find a problem, which is that you are facing like 20 text files that are saying old school format, with no graphics, with no images, no nothing. And it has an average of 18,000 text lines per file. Imagine that you have 20 of those files. Each of those files are about different sections or parts of the Tor network. But when I say Tor protocol, I am talking about all the underlying Tor protocols, all the parts of Tor that are used to communicate themselves, to set up a hidden service. They all come with a different protocol, but we bring them all together under the Tor protocol denomination. So imagine how difficult is it to go through all these files. So this is just a daunting task. So this is what motivated our work. I come from the semi-formal side of software engineering, and as I say, there was no other work in this regard. So therefore, our contribution was modeling the Tor protocol through UML. And then you may go and say, well, I studied that at university and it was fully useless. So who continues to think that? Well, if you think that, you've been deceived. Tor is useful because at the end of the day, this is a language that we software engineers speak. So if you get together with a Chinese or with a Russian, no matter whether you speak Chinese or not, at the end of the day, we will understand each other through UML. And our objective was also using the UML graph in order to see whether the models require any further design for their implementation. So we are still at the modeling phase, which is the first step to do this model verification. This I'm telling you about model-based verification that has been used before, and actually I used it through Modbus protocol, and others have used it through EMV cards. Therefore, this is nothing new. If I get the protocol and then I do formal verification, surely I will find the design flaws, which is good. What else do we have in the Tor network? First of all, types of nodes. The first one is onion proxy. That would stand for the client. You at home, you launch the Tor browser and then you become a proxy. Then we have the main element of Tor network. By default, port 9050, and these nodes are maintained by volunteers. Depending on where you are in that virtual circuit, there are three types of nodes. First of all, the guard node, which is the entry node to Tor network. Then we have the exit node, the node you use to go to ordinary web, and then the middle node in between the two other ones. Then we also have hidden service node, that is to say services only available through Tor network. Notice that onion routers will be divided in others, so this is a class diagram. And we also have directory nodes. Directory nodes allow me to obtain information about the current status of the network. Then we also have authority nodes. Well, there are only few authority nodes. There are only 10 of them, and they are selected by the organization. And authority nodes maintain the status of the network. Directory nodes obtain information, and then authority nodes will process that information and will maintain status of the network. Then introduction point and rendezvous point. So these are special type of nodes, especially when we are talking about hidden service. They are aimed at allowing clients to connect to hidden service. Then we have hidden nodes. Hidden nodes are a special type of nodes. Let us say that they are kind of a guard nodes, but unlisted. So the nodes that you use to go to Tor network are public, and they are published in a list. So if I am a state, for instance, China, and I want my users not to go into Tor network, I just get hold of the list and I block off those nodes because they are public. Bridge nodes are nodes that allow me to go to Tor network, but they are not listed, they are not public. So therefore, they facilitate connection to Tor network. What else? HS directory. So these are nodes that keep the list of hidden services that are available at Tor network. These are the nodes that the client would ask for permission to connect to a hidden service. And what type of messages do we find in Tor network? First, we have the control cell. That is to say, messages allowing me to go into a communication circuit. So here we have this type of messages: create, created, destroy, or padding. And then we have relay cell, keeping the communication flow. Communication flow goes through a Tor circuit, and then the Tor circuit may have more communication circuits simultaneously. So we start here. So far so good, isn't it? So this that we have here is a client who wants to connect to Tor network. So this is a set of steps that are followed to establish the virtual circuit of communication. we see one of the nodes being connected. This is the encrypted layer. So this is the connection asking to extend the circuit. This is the message: extend the circuit to another node. So information is encrypted with the key of the first node and also with the key of the second node. Then the second node receives this information and says, okay, I'm already connected. And then again, connection will be created with a third node. Well, how many nodes do you need to create a circuit? You need a minimum of 3 nodes on the left and 3 nodes on the right. So that is to say, a minimum of 6 nodes to go from one end to the other. So regarding internal communications, will be here. This is the message that is being set. And then external communications show on the right. So here we have very many nodes. We have created a circuit with very many nodes. And at the end of the day, we are exiting to the internet. Well, to any website. So here it tells me that this connection is not encrypted. Bear in mind that this is the node, the exit node. All the information here is TLS encrypted because it goes through Tor network. So this is, well, I have a better flow diagram than this one that I'll show later on. This is hidden service announcement. For that, a circuit is created, asking it to select a number of nodes, and then a server of hidden services receives information about all the entry nodes. This is a bit more complicated and it's a bit difficult to read. It's more complex. Okay, so what type of behaviors do we find in these nodes? By default, all nodes in Tor network follow all these behaviors. Update the network through consensus, it also updates the scripters, and it also controls the circuit. So that means when it gets a message about extending a circuit, study circuit, etc., and then user actions. All of these actions have been modeled here on the right. I'm not going to go into them, but if you are curious in knowing how often are the scripters updated, well, every 10 minutes they are often updated. Now, node behaviors. Each node or subnode will have different behaviors depending on the type of error in them. Ordinary onion routers will just send messages, and that will be it. And then, of course, locating the scripter. Authorization nodes will perform more tasks, same as directory nodes. So these tasks are related to each other. So we have the directory node informing about the status of the network, and then the authority node maintaining the status of the network. So now the anonymization. Here we designed an automatic system to access to Tor Hidden Services to retrieve information and to de-anonymize them. We have recovered some 1,800 hidden services addresses, and now out of these collected addresses, we have succeeded in binding these hidden services to 346 devices available in the visible internet system. And we managed to do that thanks to similar characteristics in them. So that does not mean that we have discovered 346 hidden services. We just said that we found services available in ordinary network that share characteristics with other services that are delivered or provided in the deep web. And because we have access to each and every one of those services, we decided to classify the content of these services. So our analysis was based on word count, and we've seen, well, we came out with graphs talking about cryptocurrency, drugs, and pornography. So pornography included everything, child porn and all type of porn. So now ethical considerations. Well, the system that we have designed is automatic. All the information was retrieved in an automatic manner, and then it was stored in a database. We primarily have collected text. We just connected our service to the hidden service. We got the HTML of the main website, and we just retrieved text. We did not collect any images. We just didn't see anything. We just didn't do anything that could be considered to be a crime. Well, I said before that I would skip a slide, and I did it on purpose because I wanted to show this diagram, because this one is self-explanatory. So on the left we have a user, and on the right we have a hidden service. And in between we have a number of routers. Each of these routers are representing nodes in the Tor network, and they all play a different role. The first one is for hidden services, a directory. The second one is an IP node, and the last one is RP node for rendezvous. Well, what does a connection to a hidden service work? Well, the hidden service, we choose a number of random nodes in the hidden network, and we'll name them as IP nodes. And it's the first step. Okay, you've been chosen. You will be my IP node. Once IP nodes have been collected, they will be sent out to this directory of hidden services. Go and say, look, this is me. I am this hidden service. If someone asks you about me, these are my IP nodes. So far, so good. Thing is, now the user wants to visit the porn site and then goes to his Onion site. I don't know whether you've seen an Onion address. It's often a very long hexadecimal address. I don't know how many characters are there in it, but let us say 64, 84, both letters and numbers. Then the Onion address is entered, and then requests will be redirected to an HS directory. Saying which ones are the IP nodes. And then it goes and says, look, I want to connect to this hidden service. And then on top of that, I want to be here. And that would be the RP node. So the client chooses the set of nodes, the set of RP nodes, where he wants to meet the hidden service. Once the HS dir tells him about the IP node, communicates this information to the IP node, and the IP node communicates that to hidden service. And what happens next? The hidden service establishes a sequence with the RP node, and from there communication takes place between the hidden service and the user. Each of these arrows stand for a Tor sequence. This is not direct communication. This is a virtual service that takes place through the Tor network. So this is a flowchart that we have designed. We have a machine there, which is the Onion proxy, which is being connected to Tor network and which is collecting addresses. It is, as I say, collecting each and every one of the main sites of these services. Basically, this is a crawler designed in C. It is there, we feed it with onion addresses, goes to onion addresses, tries to establish an HTTP and HTTPS connection, and if it is successful, information is stored in a database. So this is the collection of hidden services addresses. The second part is the anonymizing. All the characteristics and information that we go through HTTP and HTTPS, that is to say all the headers, all the metadata that was generated is stored. So in case of HTTPS, fingerprint SSL, the dates of the certificates, etc. All that information has been checked against the information available at Shodan database. Are you aware of Shodan? Well, Shodan is like a mega computer which is there listening out to everything that takes place in the internet. To consult that information, we have designed an algorithm aimed at finding similarities. After the anonymization, we moved on to categorization. That main site, HTML, with each and every of the services have been classified in four categories: drugs, sexual content, cryptocurrencies, and terrorism. And we have defined a number of key terms for each category. So in case of drugs, LSD, weed, speed; for terrorism, jihad, explosive, you name it. For each of those HTML, we tried to see whether we could fit them into a specific category. What we did here was just a word count. So this is kind of a bit ugly. We could have fine-tuned it a bit, but that's the way we did it. So imagine that I have a hidden service in the internet with very many links to Bitcoin sites. Imagine that I don't take care of that. What happens? That at the end of the day I will have lots of bitcoins. That does not mean that I'm dealing with bitcoins. However, the system will classify it as Bitcoin. So regarding natural language processing, we have used NTLK as well as Python. Experimental results. So the system to collect onion addresses have captured or collected 17,328,000 addresses. So we only successfully connected through HTTP and HTTPS connections to 1,796 addresses. The timeout set was of 30 seconds. What happens here? You can configure hidden services in different ways. You can use an ordinary Apache or an Apache which is limited and restricted to some users only. Or for instance, through access can only be gained through an encrypted key or specific certificate. And if that were to be the case, we could not connect to these hidden services either. Another problem that you may find is that hidden services often change their domain. Something that we didn't do and other researchers have done and probably will be what we will do next is to do screenshots of that home screen and then to check different domain names with the same content, because many hidden services have illegal content in them. They often change their domains. So the results are the following. 30% of those bounded to 10 devices. So we have 19.3 here of devices equaling to one device. That does not mean that that server is actually providing the hidden service. Well, perhaps we just got the server of the language and the timestamp. And many internet services contain that very same information. However, we have also had some successful cases. So regarding classification of content, these are the results. This is a list of sites per category: cryptocurrency, drugs, sexual content, and the lowest one being terrorism. Regarding the languages where we had indexes, so we also try to make a list of hidden services. The problem is that there are only 55 supported by NTLK, and we have detected 28 different languages, the most common one being English. Spanish is, well, there, appears only in 25 hidden services. Success cases. An example: the anonymization. On the left, we have the ordinary service that you find on the internet through a server, and on the right, hidden service. Notice from the very same company. So they are kind of not hiding themselves very much, but this is a result that we got from in our research. We checked that out, and actually it's the same company. Probably this is so because perhaps they have the same server providing services to the internet and also to the Tor network. Well, I'm sure you are all aware of this. Pirate Bay. So we have the hidden service here and the ordinary service. So we have just hidden all the information. Okay, we have erased all the information. Perhaps you are wondering now, how can you find hidden services in the visible web? Well, we should bear in mind that sometimes administrators of hidden services are just ordinary people. And what do ordinary people do? PHP, MySQL, Apache. So they do not configure the system well to prevent possible potential infiltration of data or data leakage. So many people try to launch the anonymization attack through direct participation in the virtual circuits of communication. So we didn't do such a direct attack. So we are not part of that virtual circuit. And many people also in Tor network, analyze what's possible to launch fingerprinting attacks based on website traffic. Many researchers are working on that. So this is an article from 2016 where a comprehensive classification of hidden services at Tor network is being offered. So this article was published in 2016. However, data were gathered in 2014. At that time, Tor 2 version was on. So with Tor 2 version, analyzing hidden services was much simpler. Two developers realized that, and then they launched Tor 3 version. Hidden services not keep an unknown address as they used to do that, but they keep a public key of the hidden address. So therefore, there is no way to know which is the address behind that public key. Well, in version number 2, everything was much easier. However, we came in 3 or 4 years late. At this point in time, for a directory node of hidden services, you have to be a node and you have to run Tor 3 version. So you cannot work with Tor 2 anymore. It and just sharing this information with you. We also have an interesting website where 6,426 addresses were collected, and they were connected to 1,174 other addresses. Well, to conclude, remember, we have worked on 2 aspects. On the one hand, we analyzed the Tor protocol and we modeled it so that we could better understand how it worked without having to read those 20 text files. I also told you about the elements of the network, the type of nodes, the type of messages, how this communication is established, the behavior of these nodes. And remember that first and foremost objective was just to perform a model-based verification. And what are we planning to do in the future? The next step should be to continue working along those lines. And not only that, we would like to get these semi-informal models, the UML diagrams, and to transform them into formal models where we could implement more mathematical algorithms with the ultimate goal of evaluating their behaviors. So here we've been thinking about transforming all UML diagram models into Petri nets to have a framework of analysis. Regarding the tool that we have developed, it is aimed at collecting unknown addresses, connecting to them, collecting data through HTTP and HTTPS to de-anonymize them. We have also established connections to 1,796 hidden services addresses, and we bounded that to less than 10 internet systems. So future improvement, several of them. We can improve the way in which we have collected all these unknown addresses. Also, one of the top problems that we find is the subsystem of de-anonymization. Thing is that we've been using Shodan. Have you used Shodan ever? Well, if you think that the Shodan database is updated, it is not updated. So we kind of have like an academic version, which I take it is the same as the paid version. But there are other type of services out there, such as Censios and others, that do exactly the same thing that Shodan. However, the internet databases are more updated. So therefore, Our primary objective should be just to change that de-anonymization to carry that out through systems other than Shodan. And then better categorization. Our categorization is very simple, it's based on words. We just get HTML, we do a word count, and we categorize it. And here we are going into semantic web. Could be implemented to check whether the website is talking about one theme or another. And then, of course, extending the range of category. And this is all from me. Thank you very much. I hope it's been entertaining. So if you have any questions, I will be around, very happy to answer. Thank you.
Creo que tenemos tiempo para preguntas.
I think we have time for questions. Don't be shy.
No veo. Ah. Espera. Si la pregunta va si vamos a liberar el código...
If the question is whether we're going to free the code, what's exactly UML? This is a joke, right? No, I haven't understood what you mean by UML. UML. What's UML? That's your question. It's Unified Modeling Language. It's the standard, semi-standard, used in the industry in order to model software systems. Thank you. Perhaps I should have included a slide with basic concepts. Other question here, and then at the back. If you study computing science, you'll suffer because you'll study UML. Have you ever thought of using some sort of fuzzy hashing for comparing the websites just by using text and seeing how close they are? No, we haven't thought about that, but we work with fuzzy hashing in memory forensic. We could try to apply it because it's basically designed for text analysis or similarities between texts. But no, we haven't thought it. It could be interesting, yes. But I'm a bit scared about the results because considering how it behaves in memory forensic, I'm not sure if it's going to be okay, but thank you. I'll give the idea. My question is related to nodes. Can you access the nodes in an invisible way? That they cannot be tracked and they are invisible, as if they didn't exist. So a node that no one knows it's there? No, because any node in the Tor network has a descriptor which is published so the others know what it is, and so that they can establish the communication through it. So having invisible nodes, except for bridge nodes, which could be invisible so that they can't be censored. Any type of social media to establish communication, for example the deep web, if you want to search for something. A social media for what? For example, if you want to find information about the state about something, I've seen in the internet some apps, and I'm not sure about that. I don't know anything about social media for that, but tried to use a server different than Google in order to find different results. They're an email service. But that's an email provider. Is it safe? I'm not familiar with it. If I access that, they could get my data. Well, use Proton Mail, which is known by the industry. The IPs of nodes, of Tor network nodes, are public, or you discover when you discover them. The exit nodes IPs. When you execute, you can execute Tor by being a proxy, so that you can be a proxy, or you can offer your computer in order to be a node between the Tor network. When you configure your PC, your computer, to become a node, you need to choose what type of node you are. If you want to be an exit node, you can face many requests, abuse requests from many companies and state agencies, because all Tor connections are going to end up in your IP, and through your IP they're going to connect to weird things. For example, Tor can use malware to send spam, and your server will be classified as spammer. That happened in one university because the configuration was the wrong one. Therefore, we could say that they're dynamic, they change in real time. The exit nodes IPs. Yes, if you go out to the normal internet, someone needs to put a face, and that's what the exit nodes do. If you want to be part of the Tor network, and I encourage you to do it, you should think where you want to be. I was thinking about defending from Tor network instead of being part. You need to think about in which part of the train you want to be.
¿Más?
Any other question? Well, you like asking questions. What's the difference between VPN and Tor? The difference between VPN and Tor. Between these two things? Well, it's completely different. VPN, it's a virtual private network. You have a communication channel in which everything is encrypted, but you know who's communicating with whom, both ends. And Tor works through virtual circuits. You have communications with many nodes, and you reach a destination, but you don't know who's communicating with whom. So the model is completely different. VPN is going to be faster. I've checked Tor, and there are plugins so that when you enter, this entry node is encrypted. Could you please repeat? When you enter, when you access their plugins, I don't know whether they do this. When you enter, then there are nodes. That node is encrypted. When you establish a connection with the first node, that connection is already encrypted. The only problem you have, and I think they've already solved it with the last version, but please check, is that the DNS request didn't go through Tor. So if someone was in the middle of the communication, could know which were the DNS requests being carried out. They could know to which address you want to connect, but they couldn't see it through Tor. They're going to know that you connected to that website, but they can't see what you see. I think there was a patch or a plugin to solve it, and it's already included in the main branch. Any other question? Well, thank you very much.